So today I would like to talk about basically some opportunities for understanding some interconnections between some of these fields. Basically, we have a listing there of several broad fields. Certainly within each of these, there is a lot of outstanding research communities, communities of excellence. But in some cases, both from an intellectual point of view, we can look at how we can connect some of these knowledge bases, and also for universities who are looking to foster applied outcomes, research flowing through into real-world applications. We do need to step back, look at the excellence going on in each of these fields, and maybe assess, to what extent it can be drawn upon, and also where there's potential opportunities between these fields that are not being fully recognized. So we're going to talk about each of these fields. So, applied data mining. So the discussion of machine learning, the discussion of artificial intelligence. One of the interesting applied aspects here is that when a given company comes to apply machine learning, the most common challenge they'll face is the actual availability of the necessary data sets. Okay, so it's not just that they may not have a very large data set, but they may not have the sorts of data that they need to build models, and certainly not deep learning models. Okay, so just general machine learning models. They may not have the necessary attributes, and all sorts of standard questions in data mining of data preparation and marshalling the data. So while we consider an emerging picture of big data, the reality is when we come to individual small companies and even larger companies, even large hospitals, they may not actually have the data sets that they need. Again, a lot of excellent work going on in the machine learning space. Just to comment on some of those trends, we certainly have an emphasis at the moment on refining the model algorithms, particularly deep learning architectures. We also have an emphasis on, in fact, building custom hardware that it's recognized that a lot of the benefits of deep learning come from essentially combining the massive data sets in some domains. In many domains it's not applicable. Certain types of problems, be they computer vision or NLP, for example, combining those with the various hardware speed-ups given by moving from general processors to GPUs. But going beyond GPUs, there's emerging focus on using, for example, field programmable gate arrays, or even application-specific chips. Okay, to get potentially multiple orders of magnitude speed up in the sorts of machine learning specific processing that's required for particular machine learning or even particular machine learning models. So these are all outstanding trends within the machine learning research community. But again, they don't necessarily find application into various practical machine learning and deployments in the real world. In addition, of course, the presence of these benchmark data sets has been a major driver of deep learning success. That is, some sorts of data sets where different parties can build models and demonstrate that they have comparative performance. Again, most of those benchmark data sets fall into the space of image processing, in other words, image and image recognition type problems, and NLP type problems, and various time series type data sets. So some of the limitations that we're facing, some of the disconnect there between what's happening in the machine learning community and applications is that, number one, deep learning is only typically restricted at the moment to certain types of problem domains. Okay, so what that means is that while many organizations may wish to apply deep learning or what they might consider artificial intelligence, again, you'd be wanting to have massive data, and also you would want to be having certain types of data. For example, image data. That's not always the sorts of predictive models that a given organization would want to develop. In addition, typical organizations have fairly limited data sets. Another interesting kind of top-level observation on the machine learning research community is while there is a lot of emphasis on refining the learning algorithms, it's been observed that often with very simple models, you can get quite a large fraction of the accuracy. So there's an interesting question here as to the comparative benefits that arise from the emphasis on the actual machine learning algorithms versus some other aspects. So, for example, data availability and various other aspects of the overall machine learning task, data mining task. So that's one very top-level view of what's going on between machine learning research and applied data mining, and we'll just bear that in mind for some of the connections that we can kind of think about just a little bit further in this discussion. The other interesting trend here is that it is the actual selection. A lot of emphasis in the data science, data analytics community is on how to select the right machine learning algorithms, how to tune those, how to select the right architecture. Interestingly enough, it's that part that is being increasingly automated. Okay, so various techniques to do automated model selection, hyperparameter selection, even taking the set of massive sets of input attributes and reducing the dimensionality of those, coming up with automated representations. These are things that are all being automated, increasingly so, meaning that the role for the data scientist may be slightly away from that center of the actual algorithm or even the selection of the algorithms themselves. So it has interesting implications for what we should be thinking about in the training of our future data science professionals as well. And of course, the move towards cloud-based engines and models. So certainly, it is the very large organizations and, for example, cloud providers who are going to have a very significant advantage in the space of machine learning. And smaller organizations will often not have the necessary data sets to actually do the sorts of learning they may wish to pursue. So, at Florida Polytechnic, we also have certainly an interest in the space of biomedical informatics, so we will touch on this particular field as well, and kind of contrast what's going on there with some of the developments of data mining. So there's a lot of excellent research communities within biomedical informatics, but they look at problems in a particular way under certain constrained paradigm. That is, there's a lot of work on developing models to predict certain canonical problems. So, for example, 30-day readmission is a very important predictive model. In the case of the US healthcare system, there's a heavy penalties for hospitals that exceed certain thresholds in terms of 30-day readmission to hospital, particularly for specific conditions. Prediction of mortality and diagnoses, and some of the examples already talked about today. So these problems are tackled and again in the research community. We have very good work coming out there. So for example, with readmission, to have a model that performs with a higher than 0.7 AUC score, area under the receiver operator curve, score is considered to be a very good performing 30-day readmission model. So through many different organizations feeding different data sets into models, doing various model selection and tuning of parameters, it's just found that there's certain limitations to what can be achieved here, and of course that is partly due to the data attributes being fed in may not be sufficient to provide full predictive information. There may be some level of randomness based on those attributes. So the point about that there is that while a lot of research goes on there within the biomedical informatics community, it comes in a certain restricted paradigm. So for example, within the cases I've just talked about, it is generally looked at, these models are all based on EHR data. And why is that? Because when you actually come to build these models, literally that is the data, these are the data sets available. Okay, so if you want to look at patient data, it may have various information about diagnoses codes or procedure codes, or demographics, admission data, transfer data, and so forth. But that's the limitations of the data sets. And efforts to build models, predictive models in that space, are kind of restricted within that paradigm. So while we talk about the idea of drawing on data from pervasive sources and non-clinical sources, in reality, we still have at least in the research community and in the real world, we have a very big disconnect between the clinical data sets and maybe what we call the mobile computing type community. Okay, so basically we don't have the sorts of data sets that combine clinical attributes with those non-clinical attributes at the moment. Hence, the problems are not tackled that way, at least in the research community and in the real world as well. So the note there at the end is that problems may be transformed if additional data is considered. So for example, just in a recent conversation with some clinicians about, how would we do readmission prediction? Again, as I'm saying, getting an ROC score of greater than 0.7 is considered a major achievement. But just as an observation, the clinicians have the view that, for example, patients who are not very agreeable in terms of willingness to comply with instructions, comply with medication, is likely to be a high factor in whether a hospital readmission occurs. So when you build these models, you do not have any attribute that represents, whether a patient is agreeable. So, there may be insights here that the attribute sets that are used, and certainly we don't draw on non-clinical attribute sets, could easily transform these problems. Similarly, if you start to draw on data that is available after discharge, potential pervasive health measures that would indicate deteriorating health, obviously that would fundamentally transform the readmission prediction problem and make it potentially a lot easier. So again, we're seeing partly due to the limitations of the data and the difference in perspective of these research communities, we're seeing a kind of a boxed approach to how these problems are being tackled. Okay, so again, it's literally it's an observation made by the preceding speaker as well, that we may not be. There is a challenge in generating this pervasive health data attributes, and one of the limitations there is that we don't currently have. It's been very hard to achieve mobile health applications and applications which actually collect the sorts of detailed attributes of physiological attributes. We can get activity measures in terms of levels of exercise and activity during a day, but that is still not really deep physiological information. And again, another limitation here is literally the technology rollout within health systems. So even the move to having electronic health records, even in the US, from the period around 2008, when they brought in the meaningful use legislation, to 2018, we've seen a move from general practitioners having about 20% EHR adoption to now 80% or more. So it's only in fairly recent times that you've seen widespread or close to universal EHR use, and certainly even moving on to the level of having clinical data warehouses is still something that many health systems are in the process of doing. So that's another practical limitation. Okay, so this is an interesting disconnect between these two particular communities, the biomedical. And one other aspect, one other limitation there is, I guess, integrating social science methodologies into some of the data mining techniques. That is, a lot of the research in the biomedical informatics community currently does actually use social science methodologies, which is tailored to the traditional survey instruments, collecting user responses, and again from very small populations. Okay, so that is at odds with various modeling mechanisms which use very large data sets, may have automated capture. So there's also an option, there's also an aspect there where that gap can be kind of closed further, so I'll comment a little bit more on that in a moment. So the final of these three broad communities I was going to comment on today and think about the links between is the mobile and pervasive computing community. So there's a lot of excellent sub-communities within this. In some ways, this community represents the prototype or prototypical IoT work, and the emphasis here is on various smartphone, wireless sensor technologies, even networking algorithms. One particular interesting contribution that this field makes, and there's many obviously, but some concept of extrapolative sensing from commodity smartphone hardware. So quite a lot of work in this community focuses on how to determine things that would be normally hard to sense but just using standard smartphones. For example, being able to do indoor mapping using smartphones, or being able to do fine-grained localization, or doing imaging in dark environments, all sorts of capabilities that basically take devices that everybody now has and allows you to draw as much inference about the environment or do as advanced sensing as possible. So that's a very valuable contribution to this overall picture as well. And of course, there's quite a lot of emphasis on novel interface capabilities, particularly in the ubiquitous or the UbiComp type community, ubiquitous and pervasive computing community. And additionally, we have broadly falling between the mobile computing community and I guess maybe more the distributed computing community. You have emerging areas of fog computing and mobile edge and mobile cloud computing. Okay, so basically thinking about where should the processing and storage occur between the edge devices and the end user devices and the cloud. So in this space, well, I wouldn't say there's limitations. Maybe the biggest limitation for healthcare in the healthcare domain is the presence of sensing capabilities that draw more sophisticated physiological attributes than physical activity and activity levels. And that may not be a limitation of the mobile computing community. Maybe it's more an aspect of biomedical engineering, but that has proven to be still very difficult. So, for example, even within that space, a problem that's considered very important is something like non-invasive blood glucose measurement. Okay, so being able to measure blood glucose levels without actually taking a blood sample. That problem itself has been tackled by many organizations, including Google, for example, and obviously many of the big biomedical companies, and even that problem has proved very, very challenging. So that is one limitation there, but one of the strengths of this mobile computing community is its ability to essentially actually construct more advanced features from some underlying raw data, okay, raw sensing data from an environment, from a person, and being able to infer higher level features from that which can potentially be fed into models, into predictive models and data mining processes. So again, the sort of intellectual exploration being considered here is to draw some links between these broad fields. Okay, and one of the implications is that even though there is an emphasis currently on big data and an emphasis on the pervasiveness of the IoT, when you come to practically try to tackle a data mining problem, what you find is you don't have the data set. Okay, so there's a kind of an interesting disconnect there. So at least one kind of consideration, one implication of this is the idea of having a greater emphasis on connecting the end-to-end picture here, which is when constructing an informatics system or constructing an IoT system, what data may be needed to help build a valuable predictive model, okay? Instead of collecting large quantities of data and then finding that it's very hard to build the predictive model. Okay, so that you might say, well, that's easier said than done, but there's various avenues that suggests. So again, it's the idea maybe to start with the valuable predictive problem that you wish to solve, and then consider how to go about deriving systems that obtain those sorts of attributes that are needed for that. So one of the implications of that is that for IoT system design or informatics design, it is highly desirable to have very reconfigurable systems in terms of what can be captured, in terms of whether it can be reconfigured to obtain the certain types of attributes that you may wish, or you may change over time as you decide to vary the sorts of models you wish to build. So one interesting example here, and this is a research space or research subspace that's attracted a little bit of attention over the last 5 to 10 years, I guess, in total. Maybe originally referred to as participatory sensing, and maybe more recently as crowd sensing, which of course is having many users with their devices each capture certain data which contributes to some aggregate data capture task. So the reason that that's an interesting example is that smartphones in many ways, or smartphones and attached sensors, particularly in the healthcare space, may represent the most widely deployed and advanced sensing system that we have. But combined with their human users in a crowd sensing type of fashion, they also represent highly reconfigurable sensing systems, if we can put it that way. So the individual can choose to use their device. They can take a manual action to obtain certain information, to use the device in a certain way, to make a measurement, or even to manually provide certain feedback. So within the crowd sensing space, we have an emphasis on in the research field on how to actually drive activity of individuals to participate. So various ideas of incentives. These may be monetary, but the general, there's a lot of research in that space that looks at how much individuals have to be paid or reimbursed to take certain actions. In other words, there is research to look at how to start to drive particular attribute capture. Okay, so just to try to tie together a few pieces here. Number one, that when you come to practically undertake data mining, you find you don't have the data sets that you need. At the same time, we do have widespread deployment of sensors and smartphone type systems, and we have such techniques as crowd sensing, which allows us to reconfigurably drive certain data capture, to drive that model creation. So in some ways you see real-world examples of that even in what Google does when they're asking you to provide ratings or provide image recognition, the recapture type techniques. So they have certain goals they have in terms of deriving labeled data sets, and they're employing the population to engage in that data set construction. So similarly, there's a raft of techniques here where you can think about how to start with the end in mind, basically to start with the sort of models that you wish to, what you consider valuable predictive models, and go about constructing those data sets. Okay, so a particular sub-aspect of this that we're looking at is the space of health crowd sensing. Okay, so this is the idea of basically incentivizing groups or individuals to provide health data, again looking at it from the perspective of some sort of reimbursed activity, and also to look at it in terms of collecting that data on specified subpopulations. So for example, in some cases you may wish to collect data from a certain demographic. So for example, males between the age of 30 and 35. So you might be able to, and you may have a total budget with which to collect that data. And so some of the ideas that we're thinking about is how to obtain certain attributes that are desired for particular predictive problems in a sort of a specified way, and possibly in thinking of it in terms of what are the algorithmic mechanisms, what are the incentive mechanisms required to derive that sort of data capture and sort of work from the end goal back to the data capture goal. Another aspect that we're looking at in this space is the space of fog layer analytics. So again, the idea of the fog layer has a role to play in the sort of machine learning topics we're thinking about here. The fog layer being nodes that reside closer to the network edge than the cloud, where you can do certain local data capture, local processing. So particularly in the case of predictive model building, you may wish to do the inference stage where you're actually doing classification of given examples, where you may wish to do this at a quicker rate. This may be the case in certain health applications, but with lower latency and more close to end sensing devices. An aspect we're looking at is this is a broad topic, but there's architectural, there's advantage in employing those sorts of architectures. Another observation here is again this topic that's come up today, which is this interesting question of the limitations of EHR-derived models and drawing on the data that's outside of a clinical setting. Okay, so the kind of implication there may be that in certain ways to pull attributes from patients when they're in a non-clinical setting in some sort of incentive-based way may provide a way to build much stronger models than typically derived in the existing paradigms. As I say, using all attributes available in EHR data, it is commonly experienced that certain ceiling of performance is achieved in terms of its predictive capability, whereas if you draw just minimum data attributes from say a post-discharge scenario or from a non-clinical setting, those problems might be able to be fundamentally transformed, or even the whole question of readmission possibly re-examined, whether that's an appropriate measure for assessing health organisations or penalising them. So there's a lot of opportunity there, and I guess what we're suggesting is that there may be ways to try to derive those data sets in a way, using a technological approach, but using a kind of using an innovative approach, an innovative paradigm of how to look at that particular problem. Similarly, this applies to collecting data attributes that are from a clinical setting as well, which are not typically collected in EHRs. So, for example, I gave a point about clinicians observing that a patient who is not very receptive to following instructions might be considered a readmission risk. Okay, so in this particular space, there's the ability to draw additional attributes into the data set that are, for example, manually retrieved or clinician retrieved, that are not in the standard data sets, that are not part of the standard EHR, and basically in that way, again, advancing predictive model performance by working backwards from the data collected, rather than just trying to take the set of attributes and refine the models, do more advanced feature engineering and so forth, and that appears to have its limitations from the literature. So, in conclusion, really what we're covering here is to say that we have some very outstanding individual research domains. The three that I listed have many rich subject communities of their own. A lot of the strength and the great results coming from deep learning, from mobile computing, comes from their focus. What we're suggesting here is that there's also a role to be played by stepping back and looking at the total contribution that each of those fields can make, and how, considered together, they, there may be a slightly different paradigms that can be adopted, and also to stress that it's those sorts of insights that are not just important from an intellectual university research perspective, but also, as I've emphasised here, in terms of building real-world data mining models, the question of data availability is really a driving factor. So in terms of getting applied results, applied innovation, this sort of stepping back from the individual research communities and taking a holistic approach is something that is basically being touched on in this talk. Okay, thank you.